start. Welcome to the first breakout session of today, Wednesday, the second day of the NDN Conference 2014 here in beautiful Uppsala. The session is called Transport Networks, and we're diving down deeper into the stack. For those of you who were here yesterday in the Innovation and Network session, this session we have three speakers with, I think, three interesting topics lined up for you. We're going to dive down into the lower layers of the network and the advances in the lower layers of the network. Our first speaker is Henning Hintertür from Adva Optical. He's based in Germany and he's the product line manager for optical transport products from Adva. Henning has 15 years of experience in the optical business and he holds a PhD in quantum optics. That's mind-boggling for me. Henning, the floor is yours.
Thank you very much, Rakan. Corrections and things like that would have to be stripped away before you can really look at the payload of a signal and start listening some relevant data. So it was a common sense that this must be something very complex or even very expensive to do, and nobody would seriously do that. So this view over the last 50 years has really changed radically. So, I mean, you see this copy from the YouTube internet basically. You all know what's going on in the press and what's going on in the real world. Technology has massively evolved. Today you find optical networks everywhere. You don't need to run a submarine to find an optical network. It's everywhere, in the regional networks, in the metro, in the access. WDM is present everywhere and optical networks are present. So also the risk that somebody goes there and spies is of course much higher. Technology has proven to be much lower cost today. So the good side of that is that you see more and more vendors coming up with integrated technology. You can buy encryption schemes in layer 3 machines and layer 2 machines. Layer 1 is the topic here today, so encryption can be integrated on the layer 1. So is not so big as it was 50 years ago because the technology is so cheap today. Encryption, I would say, doesn't bring a benefit to each and every optical network. But there are some networks where the benefit of encryption is huge. And those are typically the networks where you see a consolidation of multiple services that are considered mission critical for this particular network operator. And this is typically the case for data centers. So let's have a look into data centers. In the end of my talk, I will give you an overview that shows where encryption is mostly used in optical networks. You will see it's mostly data centers today, with a tendency to maybe move also more and more into infrastructures. But let's first have a look into data centers and the security concepts in data center networks. So first of all the major data center operators, network operators in data centers, of course they have security concepts today. The first thing they always do is they protect the buildings. So all the buildings are typically shielded against any kind of attacks And in doing this, they basically protect their hardware inside the data center. So there are gateways that make sure that only selected people can enter the data center, buildings are shielded, and in doing that they prevent basically their setups from reconfiguration, malicious use in any way. So the hardware is secure basically. But what about software? All the applications running on those hardware machines, also here data centers have very sophisticated security concepts, so things like secure shells, for example, separated IP domains. They have authentication servers, for example, to make sure that only selected people can get access to the machines. They track when somebody is logged in, and they have rules how long you can be logged in. They have regular password updates according to certain rules. That's basically all in place. But the point where all these nice sophisticated schemes are basically failing is the point where the fiber leaves the building. Because when they are setting up networks between the data centers, the fiber is leaving the building, is leaving the campus, and typically always has to go over public ground. And now even if the data center operator is owning the fiber, he's sort of losing control. He cannot apply his usual security concepts to a dark fiber or to a leased fiber that is going over public ground. And this is where the problem is basically coming up. This slide is about where can you tap fiber and how can you gain data out of the fiber tap. So basically, in order to maintain fiber infrastructure, people have invented something like a street cabinet. So every fiber operator today has street cabinets. We know all these gray cabinets at the streets, and you can imagine that it's relatively easy to enter such a cabinet, break in, get access to a splice box, get access to a group of fibers that is running through the splice box, and that may be carrying in services based on some wavelength scheme. That's not a difficult thing. And then, as soon as you have access to those fibers, you have two choices. You can either deploy the so-called Y-bridge, you see it in the picture, which is a very small device, and hope that nobody detects this Y-bridge. And you can permanently tap the light basically going through this fiber. Or you can run a so-called fiber coupling device, which makes use of the well-known bending effect in fibers. That means when you bend a fiber, a portion of the light is typically leaving the core, and you can detect this portion of the light and start tapping the signals. And in doing this, you would even have a method to tap light non-intrusively. People can't detect this, basically. And then the next step, if you get access to the light, would be you just apply a device that you can buy from, let's say, JDSU for some amount of money to analyze the protocols, to strip away the transport protocol headers, which are fully standardized. Everybody knows everything about those headers, and you get access to the payload of the signal. So that's basically the way how you can tap optical networks today, and we know that this is taking place today. People are doing this. Okay, so let's talk about encryption. Let's assume I'm a network operator and I'm interested in increasing the security level of my optical network. I want to run encryption. What are the key parameters I have to look at in order to make the right judgment and in order to make the right choice for a specific encryption scheme? Just high level, this is, I think, pretty straightforward. I want something that provides a high level of security, of course, and this is important because encryption has a long history. There are lots of different algorithms out with different performance. Yeah. Some have a track record in terms of hackers found a clever method to get access to the scheme. Others have never been hacked. Yeah. So you have to look also for this history, and you have to make the right selection on an encryption scheme. Then encryption schemes also have a certain performance in terms of how do they affect the data. And here, of course, you would like to have minimum impact to your data transmission, to your services. That means lowest latency, 100% throughput. You don't want to cut throughput from your actual services just in order to manage your encryption scheme. And basically, the jitter impact should be minimum, of course. And finally, if you are a carrier and interested in offering services to your end customers, it might also be interesting for you to be able to prove that this encryption scheme is now running on this link and basically sell a secure link to an end customer. Yeah, that may end up with some role-based management where your end customer gets access to the security settings of the link, whereby you as an operator are still maintaining the connectivity, data rates, wavelengths and things like that. So a role-based management scheme may be interesting as well. In total, at the bottom line, you will come to the conclusion, in order to achieve those objectives, it's always easiest to run the encryption scheme on the lowest possible layer in the OC model, basically. So ideally, that's layer 1. But of course, it's not always possible. Encryption schemes, as I said, there are many different schemes available. There's also an evolution in terms of encryption schemes. And it would be beyond the scope of this talk, I think, to introduce you to the world of encryption schemes. Maybe just a few words on the security level. You see it on the slide. AES-256 is, I would say, the predominant encryption scheme that is widely used today. And this encryption scheme has proven to be very secure. So there is worldwide, nobody could find a systematic approach to hack in AES-256. So basically, the only way to crack this is at least a common opinion, trial and error, basically. And now trial and error can be something very complicated, because you can imagine the complexity of such an encryption scheme always scales with the length of the keys that you are using. In the digital domain, keys are always numbers, and numbers can be very large. So if you really have only this trial and error method to hack an encryption scheme, you need many, many choices until you can get successful in hacking an encryption scheme like that. And in the case of AES-256, you see this nice graph. The number of trials you would need in order to be reasonably successful in hacking that is similar to the number of atoms in the universe, just to give you a feeling. So it's a very large number. And trial and error is certainly not a good method to hack that, so nobody will do that. Encryption on different layers. So you might have heard about layer 3 encryption, IPsec. People talk about MACsec on the layer 2. I'm going to talk about layer 1 encryption here. So what's the difference? What does it help me to switch between the different layers? The first and most obvious difference when you're doing encryption on the layer 1 is that it's inherently protocol agnostic. So if you're running a transport card in a system like an OTN card, for example, this card usually is a multi-service card. It can run all the Ethernets, but it can also run standard SONET SDH, fiber channels, any kind of data protocol. And this encryption scheme that is running on this card is basically agnostic. It doesn't really interfere with the payload protocol. So therefore, layer 1 encryption can always be applied to multiple protocols. And that's sometimes very interesting in the data center world, especially because all these classical data centers running large SAN environments have a great multiplicity of different protocols, and they have to cope with it. It doesn't help them to only encrypt in Ethernet. It's not a solution. The second difference between the different layer encryption methods is you have to understand that encryption schemes today are always dynamic. That means the keys that are applied to the encryption scheme frequently change. And in order to have a dynamic key exchange scheme permanently running on an encrypted link, you need to exchange some data. Data that is only for the purpose of running this encryption scheme and running the key exchange. That is data that is automatically created by the encryption scheme in itself. And in order to transmit this data, you need capacity. So now when you go to the protocol encryption schemes, like for example in IPsec, and you see some examples on the slide, in order to create capacity for this encryption scheme, you need to add some header to the protocol. So for example in IP, for every IP packet that you want to encrypt, you need to add something to this IP packet just in order to manage your encryption scheme. And for layer 2, it's the same story but a little bit different. So what does that mean? It means that you are eating up the throughput of your protocols. Because you cannot just increase the data rate of your Ethernet signal, you are tied to the standards, of course, and adding overheads to the packets means basically, essentially, you cut down the throughput in some way. This is not necessary for layer 1 encryption, because with the layer 1 transport protocols, and the most famous example, of course, is always OTN, we have already overheads in the OTN bytes that can be used for such a purpose. So we basically, in order to maintain a dynamic encryption scheme on an OTN link, we would just go to some free overhead bytes, and we are pretty flexible in this choice, put our encryption scheme into those overhead bytes, and the payload would see nothing from it. So the payload is still 100% transparent. We just turn some idle pattern into something meaningful to manage the encryption. And I'm coming to that in more detail. So that's another advantage. This problem of cutting down the throughput in protocols is visualized in this graph. You see protocol throughput as a function of frame size for different encryption schemes. What is called the ADVA encryption scheme here at the top, the straight line, would be a layer 1 encryption scheme. That would be the same for any kind of layer 1 scheme. And then you see some different examples for encryption schemes that are predominantly running on layer 2 or even layer 3. And you see, basically it's always the same picture. There's some kind of breakdown in the throughput whenever your packets get smaller and smaller. And that's just due to the nature of the problem. You have to add this overhead for every packet. And of course this becomes more severe when packets get smaller. So typically, according to some public studies, the typical size of a packet on the internet is like 300 to 400 bytes. So we would be in this area right in the middle of the graph with some, let's say, roughly 20% hit to the throughput of the signals. Yeah. If we were to apply layer 2, layer 3 encryption scheme to everything in the internet world. Okay, I'm here to talk about layer 1 encryption. Let's look a little bit more closer at this layer 1 encryption scheme. So what you see at the bottom here is a typical OTN frame structure. It could be, let's assume it's a 10 gigabit OTO2 frame, for example. This structure has some hierarchical containers, and you're familiar with that. It's O2, ODU, OPU, and then we have some payload signal. And then, of course, the forward error correction is carried in this OTU overhead as well on the very right-hand side. So what are we doing here? Fundamentally, of course, we must not encrypt this header, because the header is usually used in the networks to manage the networks, just roughly speaking. So the only thing we encrypt is the payload. You see it at the bottom here, encrypted payload, and we use some parts of the headers of the protocol to maintain the encryption scheme. So after the encryption, the frame, the OTN frame, is still a fully 100% standard compliant frame. Yeah, it can be run through an OTN cross-connect, for example, with no compliance problems. Forward error correction is still running as usual, no effects. The only thing that changes is the complete payload is encrypted, and some of the overhead bytes, and essentially that's the GCC2 we are using here today, carry some bits to do the key exchange. So let's have a look at the encryption scheme a little bit more from a networking perspective. You see the two locations. In this case, it's just some photos from some ADVA boxes. So what do you have to do to run an encryption link? And here we are, of course, we are talking a modular system. The system typically contains something called channel cards. Channel cards creating individual wavelengths with transport protocols, running any kind of data protocols. And the encryption schemes are running on those channel cards. The first thing, though, you have to do to make this system running on a point-to-point link is you have to make sure that the right two guys are talking to each other. And this is called authentication. So you first have to bring up an authentication key to the two NEs, to the two units at the near end and far end, to make sure that those two units are allowed to talk to each other. And then the whole system comes up automatically and starts a dynamic key exchange encryption scheme where AES-256 is basically the fundamental underlying algorithm to create the security level. In order to maintain the key exchange, there are also different schemes available. The scheme we are using here, and this is also pretty popular, is a so-called Diffie-Hellman, where we only exchange some key integer numbers over the link, random numbers of course, to get the remote location, to basically enable the remote location to generate keys on its own, rather than transmitting clear code keys over the link, which of course is not allowed. This key exchange typically happens, depending on the configuration, once a minute or once every 10 minutes. So the key lifetime is configurable. The whole scheme adds some latency to the transmission, but it's in the order of 100 nanoseconds. So it's completely negligible, for example, when you compare it with a forward error correction scheme or something like that. Some pictures of channel cards, I don't go too much into the details. So basically this is a picture of a channel card. You have a typical architecture, client ports where you attach your Ethernet, fiber channel, whatever kind of signals. Then you have some remote or networking ports that are typically, in this case, running on 10 gigabit. Everything is pluggable. And inside this module, you see this red box at the bottom, where we are in the electrical domain anyway and do this mapping and multiplexing. We just add an encryption scheme to that procedure. That's the whole idea. This is just another example of a 100 gigabit card. So we are the first vendor coming up with encryption schemes for 100 gigabit on the layer 1. But basically same procedure. Again, you see this red box at the bottom. In addition to the standard GMP G709 mapping procedures here, we add an encryption scheme to the whole 100 gigabit OTU frame. So the whole frame is basically the payload of the whole frame is encrypted. So what can we offer here in terms of services? For the data center customers, we are only offering those two types of cards, a 10 gig card and a 100 gigabit card. And with those two universal cards, we can address the whole set of services basically. Everything starting from 1 gig, be it fiber channel or Ethernet, up to 100 gigabit Ethernet. It's all covered on the same two designs. And of course, the lower data rates are typically run on the 10 gigabit solution, whereas the higher data rates in green are typically run on the 100 gigabit cards. Yeah. So for example, just a concrete example, somebody is running 16 gig fiber channel, he will buy a 100 gigabit card. You see at the top, he can multiplex 16 gigabit fiber channel 7 times into an OTU4 frame, and this OTU4 frame is encrypted. Management solutions, I said it briefly in the beginning, so we want to encrypt networks, but we also want to bring operators into the position to sell encrypted services to end customers. And therefore, we have developed a management solution that is layered. So in this scenario, number one is the easy case. I don't want to go through the details. You see a network at the bottom. Let's assume this network is now running encrypted services. Then, of course, we have management systems running all these NEs, visualizing the network, and also running the encryption procedures and visualizing the encryption procedures. The more complex case is this one here, scenario number 2. Let's assume that there is an end customer, customer A, sitting behind some firewall, and this customer now gets an encrypted service from the operator at the right-hand side. In this case, we can basically split the management roles into two areas. The one area on the right-hand side still continues with all the networking aspects. So the operator can still see the complete network, configure data rates, manage wavelengths, and all this user stuff, but he doesn't see anything about service encryption. Whereas on the left-hand side, the customer can see the service encryption. He will see the key exchanges. He can see if a key exchange fails. He can see how old the passwords are he's running. So he basically sees the performance of the encryption, but he cannot see the entire network. So he doesn't need to cope with anything that is related to connectivity. Another important aspect is this one here. Since, of course, encryption is also interested over long-haul distances, and here we are very often facing multi-vendor scenarios, it's also interesting to offer this encryption scheme in a way that it can interoperate with any kind of third-party backbone network, for example. Yeah? And due to the nature of OTN, this is possible. Yeah? Of course, all the vendors in the world support the same standardized OTN client ports, and you can just connect such an encryption card to such an OTN client port and then run the entire encryption protocol end-to-end over such a third-party backbone. And this is not straightforward, it's really a specific feature and it's only working because the encryption is implemented in a way that such an OTN network can be completely agnostic to the whole dynamic key exchange. We are basically able to completely hide the key exchange from all the active OTN networking functions and terminations in the third-party network. That's basically the same picture, but for a 100 gigabit application. So here we hook up the 100 gigabit OTO4 port directly to the client port of an OTN carrier network. Okay, my last slide is this one here. It's a little bit a market slide. So who is really interested in encryption? Where do we typically deploy this? You see in the bar graph, this is about which sectors, which industry sectors did the highest spendings in security. But that's not just optical layer security, that's basically everything. And you see different industries like government at the top, and then all the other segments you can read on your own. And then in the boxes you see where we are typically selling optical layer encryption today, or deploying optical layer encryption. This is not exactly following the bar graph diagram, because it's also due to the question who of those guys is really running optical networks, who owns optical networks, and who's really interested in finally doing layer 1 encryption. But basically it's there. We are running today like around about 10,000 commercial encrypted services that have been deployed over the last 2 years. Thank you very much.
Thank you. Thank you very much, Henning. We have time for 1 or 2 questions. Question for Henning? Quick question for me, Henning. You just elaborated on the fact that your company can now do 100 gig encryption on the optical network. As we're already moving or thinking to move to higher speed than 100 gig, either using FlexCrypt or not, you hear about 200 gig, 400 gig, people talk about terabit lambdas. Do you think it's scalable into the future that you can do encryption at line rate at this higher speed? So where do you see the limits?
Okay, yeah, thanks for the question. I think you saw that we are basically, what is the framework of our encryption? Yeah? Is it somehow limited to data rates? And I would say no, it's not. The framework relies on OTN containers. So as soon as you have such a kind of virtual container structure on your 400 gigabit wavelength, and I think we all believe there will be something like this, yeah, then you can basically maintain the same encryption scheme with the next generation of data rates. Yeah. So I don't see any restriction to that. Saying that, our customer base today is very much in the data center space, and those guys are just moving to 100 gigabit as we speak. Yeah. So I think the lifetime of the 100 gigabit encryption is still 2 to 3 years to go now.
Okay, thank you. Thank you once more, Henning.
Thank you.
For an interesting presentation. Right, we're right on time, and we go to the second speaker of this morning, in this breakout session on optical networks. Our second speaker is Christophe Oldrati. He's a telecom engineer who got his education at the École Supérieure de l'Électricité in France. He holds a master's degree in radio communication, and he is at Siena. He's at Siena EMEA, and he's an optical packet engineer with 20 years of experience in this industry. And as soon as his slides are up, the floor is for Christophe.
All right, thank you, Eric. Thanks. So delighted to be here talking to you today. So I guess we are all aware that transport networks are being challenged today, and the way we are used to deploying transport network is really being challenged because of the increasing demand of capacity, but as well because of the unpredictability of the traffic and the growing demand for traffic that is not always on. So I found pretty interesting actually this morning to see two examples of this, either from the seismic presentations where we were discussing how we can efficiently share all that data, and the fact that well, you probably need to be very rapidly able to access that data in a way that is completely unpredictable, because it's pretty difficult to predict when that earthquake is going to happen. But as well in seeing how what applies to the challenges of Wi-Fi network in terms of, again, growing demands and expectations from the end customers applies as well to metro and long-distance transport networks. So the challenges come, of course, from the increasing demand for data, and we are talking about something like 30%, 40% increase per year. But as well, the key aspect is that unpredictability of traffic. So we moved from a situation where we had traffic more or less always on, connecting places to places, to a situation where we started connecting people to places, those people being mobile. But then now those people are connecting to servers, mainly servers, applications that themselves are being mobile, moving from a data center to another one. The applications themselves are moving as virtual machines from a data center to another one. The stored data is moving. And as well, in addition to all this movement, we are seeing a lot of traffic that is not always on. So if you're well, just looking at the amount of data that you might collect in a research experiment from the CERN, that is required to be moved externally to a data center. That doesn't happen every day, but when it happens, you need that amount of bandwidth to really make it happen. And in the same way, you don't move virtual machines every second, but when it happens, you need that bandwidth to be here and with a proper quality, because it is a kind of application that is not very resilient to losing packets, having very high delay. So basically, we need to transform the optical networks to make them far more agile. And well, I would say somehow shame on us, the transport industry. In the past years, we haven't really kept up with the trends toward more virtualization and agility. If you're looking at the global network, there are mainly three main components. So you have the compute resource, really all those servers, the virtual machines. You have the storage of data, which in itself is a very big and demanding component. And you have the network that connects all these two together, so the transport network. And as of today, and if you have a big enough credit card, you can pretty much purchase very rapidly some additional compute capacity from Amazon, Microsoft Azure, or any of those cloud vendors. You can purchase some storage capacity on the web pretty easily. But what you cannot do is get the capacity on demand that you require to connect your users to these data centers, or the two data centers together on demand. This you cannot do. Either you have planned for that bandwidth to be available months ago, or you will have to wait for weeks or months for the network to be able to put in place additional capacity. So we really need to evolve into making the connect part of the network part of the global virtualized network, to really be able to derive the benefits from this global virtualization. And it's not an easy task, so it's taking a lot of different components. Mainly the way we are looking at it is on 3 components. So starting from what's up there, you've got really the applications themselves, which are not really part of the transport networks, but these are the applications that run on the data centers, and it can be virtual machines, for example. But those applications need to be able to drive the transport network on demand according to their required SLA bandwidth and the time at which they are going to be activated. So what sits between those applications and the infrastructure itself is really that controller, and now we are in this wonderful premises of the SDN world, where we have this controller with a proper software to be able to interpret or receive requirements from the applications and drive the transport network. So this is progressing well, and especially on the transport networks. Also, it's not, I wouldn't argue that it's here, it's completely in place, but it's making good progress, and I'm going to discuss a few of the specific applications that we can use for SDN in the transport network. But what's important as well is the last part, at the bottom, the infrastructure as well. So the buzz today is really on SDN, and let's have that software and everything will be fine. So let's remember, of course, that the software, you won't be able to do anything with it if you don't have an agile infrastructure. And the hardware still has a lot of value, and the hardware needs to be agile. It needs to be able to switch, to protect, to reconfigure services. So it's a very important part of the complete agile network. So let's look at this hardware first. So we are discussing mainly 3 parts in the transport network. So the photonics at the bottom, which deals with, am I able to reroute that wavelength from maybe a short link to a very long link now? So do I have the ability in the amplifier, in the wavelength equalization scheme to rapidly reroute wavelengths? So we have the transmission itself, the line rates. So how am I going to keep pace with that growing demand of bandwidth? So going from 100 gig today to 200 gig, 3-port channels, etc. That's an important part in keeping that agility as well. And the last one at the top here is all the switching component. So how am I going to provide the required flexibility in the way I handle services? And the different kind of services, so be it services that are really, I would say, small capacity data services, or more high capacity fixed bandwidth OTN services. So for all those kind of services, I need to be able to have schemes that allow me to properly aggregate the services, route them, protect them with different SLA schemes. And this is really provided by the switching part of that infrastructure. And all those components, of course, need then to be controlled by that SDN controller. So well, it's a pretty ambitious subject to deal with in just 25 minutes, of course. So I'm just proposing to focus on a few subjects where the technology is advancing in those areas. So packet optical. This is a key trend that we are seeing in the transport industry. So earlier this year there's been a study where the question was asked to service providers on how they see this evolving. And the outcome of this is that people expect that the number of packet optical transport devices will be probably multiplied by 3 by 2016. And we have about the same figure multiplied by 3 when you look at where the packet services are going to be carried. If you compare with packet services being carried over routers or directly on transport platforms with packet capability. So very big trend into putting into that transport platform packet handling capability. So this really, now that gives us several technologies to efficiently handle the different kind of traffic, MPLS, TP, Ethernet, and OTN. And let's make it clear, packets, so Ethernet, MPLS, TP technology, these are transport technology. It allows us to aggregate the traffic, to protect the traffic, to carry synchronization. It has the proper OEM capability to control the quality of the link, performance monitoring, and all of this. So these packet capabilities are really evolved now to being something that can be used into transport networks. So that gives us really the tools to manage the services as a proper layer. So again, services that will benefit from the packet statistical multiplexing scheme can be handled on packet fabrics, and services that are more bulk services that require high capacity, very resilient network will be handled at the OTN layer. But all this inside the same box, inside the same switching fabric that can handle both packets and OTN switching. So these are the tools that we have now in our equipment, and I guess, well, it's again something very well accepted that you always need to handle the traffic at the lowest possible layer for simplicity and for cost efficiency. So again, this is what those packet optical platform give us, the ability just to select the proper technology to handle every kind of traffic. So really the way we have been building networks in the past year is really to consider that services were required to go through IP routers. And unfortunately, those services at each intermediate point in the network, most of the time, were going up to the layer 3. And in most cases, they had nothing to do with the routers because it was just pass-through traffic. So the router was unfortunately used as a regenerator. And that's it. And the optical layer was just providing the bandwidth to transmit between two routers. So this doesn't scale anymore. As the bandwidth is growing, the routers, or the cost of the routers is really exploding in networks. So we need to keep the routers for what they are good at, and not overload those very high-value interfaces or high-cost interfaces, I might say, with unnecessary traffic. So that's really one of the promises as well of those packet optical networks, where you are able to use the packet capability to do the proper final aggregation of traffic and protection of traffic, which allow us now to pass through traffic at the packet layer and avoid intermediate routers. So that's something that has been done for a few years at the wavelengths layer, with ROADM, express wavelengths, that's stopping in the routers. But now you can do it at a much finer granularity with packets or with OTN. Okay, so this is another tool, again, to optimize globally the networks layer 0 to layer 3. One example of this is a network, actually, an NREN network that we have deployed at the beginning of this year. So when we looked at the network, we compared with the traditional way that was used in this network of handling traffic. So putting intermediate routers everywhere, with using OTN aggregation and expressing. So when we did this, we already saved around 14% of the bandwidth that was required at the transport layer by using the OTN capability. Now going forward, we added packet switching capability in this network, and now this leads us to saving 34% of the bandwidth required. So 34% of the transmission bandwidth, but as well much more on the interfaces that you consume on the routers. So definitely this is happening, and this is bringing a real interest into the way we build networks. So that's dealing with with the switching aspect. So the next question is really the raw capacity. How do you handle this growth of raw capacity, and what's happening beyond 100 gig? So we are pursuing 3 evolution paths to go beyond 100 gig. So the first one, going to the right, is how do I increase the baud rate? So today, using QPSK, you're typically in a baud rate of around 25 gigabaud per second. So we need to increase that. That really is still a long-term objective, and it's still, I would say, a few years before we can really go to the next step of the technology, increasing a lot the baud rate. So what is more promising in the short and medium term is the other 2 axes. So the one going up is using different modulation schemes. So we have now a full choice of modulation schemes. And the interesting point now is that we have the flexibility with those modulation schemes to play on performance, so reach of the wavelength, versus spectrum efficiency. So for example, if you use the BPSK modulation scheme at the bottom, so you have a spectrum efficiency that is less than with the higher modulation schemes, but then you have a very high OSNR tolerance, which means that this can be applied to transport networks reaching now something like 14,000 kilometers without regeneration on submarine networks. Now, if you don't need that reach, then you can start climbing the ladder into modulation schemes, going into 4 QPSK or 16 QM. And when you reach 16 QM, it means that within just 50 gigahertz, you can transmit 200 gigabit per second. And of course, you will not go 14,000 kilometers, right? We're more in the 1,000 kilometer range. But then you can start playing with the modulation schemes, so capacity versus reach, and as well versus latency, because within that same ASIC that we have, we really make the wavelengths something that is programmable. So again, you can decrease the FEC that you are using, so decrease the latency of the signal if you don't need to go the whole maximum range. So you start having that agility in the waveform. And the last aspect is the ability to do support channels and pack more capacity in less bandwidth. So this is just an example of what you get for 400 gig transmission, going from today, where you take 4 times 100 gig, so 200 gigahertz of bandwidth, going into using 200 gigabit per second traffic wavelengths with 16 QAM, where you will use only half of that bandwidth, so double the spectral efficiency. And the next step is using support channels, so packing that capacity and carrying those 2 wavelengths into just 75 gigahertz of traffic. So this is a support channel trend that is happening now, so increasing the spectral efficiency. So now we have challenges, of course, when you go to higher modulation schemes and more spectrum efficiencies. This is the first experiment that we have on what we are going to get 200 gig, and we'll have productized 200 gig at the end of the year. We are already using this, by the way, for terabit demonstration, but it's really, we are really making a product at the end of this year. So this is the expected reach of a 200 gig wavelength using 16 QAM on a 50 gigahertz grid. So we are in the range of the 800 kilometer, let's say, with standard ETFA, and we are going to be able to increase that rate using more Raman amplifiers, so that you can get a better OSNR on the wavelength. But that's still something that is very applicable to regional and, well, most long-distance network in Europe, I would say. So now, the interesting thing is that as you go to those modulation schemes, you will need more and more OSNR. And the Shannon limit, by the way, is telling us this. So we expect actually to deploy more Raman amplifiers. So now we need to make Raman easier to deploy. So you know that we have some constraints with Raman on the quality and no reflection in the first kilometers. So we have put a lot of software in our Raman amplifiers, integrated an OTDR, so that it can check the quality of the fiber before you first put it into service. But as well, after a break, you're able now to detect directly where the break is on the fiber, and after it is repaired, after the failure event, revalidate the quality of that fiber. So that's just an example of a 1 terabit experiment that we did at the beginning of this year with Comcast. So in this case, it was on a 1,000 kilometer ELIF fiber. So as you know, ELIF is really not a preferred fiber for coherent transmission, but nevertheless, this is what was used here. And we were using 5 200 gigabit per second wavelengths packed into a 1 terabit super channel. And this was running alongside a 10 gig, 40 gig, and 100 gig. So now transmitting 1 terabit over 200 gigahertz of spectrum. So that's the kind of thing that we are doing. This applies as well to submarine networks. And we are introducing now technologies to submarine networks to help make them more agile as well. Introducing ROADMs, which were not commonplace in submarine networks. Starting using these super channels to efficiently manage the spectrum on submarine cables. And you might know that on submarine cables, you always find out, especially on older cables, that some pieces of this spectrum is better than other ones. So you want to leverage that by packing more capacity in those slices of spectrum that are good. So that's increasing the capacity into submarine networks, and as well bringing more automatic chromatic dispersion capability into those networks to be able to reach those transatlantic links. So this was discussing really the infrastructure. Now if we are looking at that SDN controller, that's a key point, I guess, in making things different from what they used to be. Because one of our key objectives with the SDN controller is really to start doing something that is fully open. So for that, we are going to use the Open Daylight open source software to build our SDN controller. And the objective of the SDN controller is really to have something that is open across layers, layer 0 to layer 3, across vendors, multi-vendors, and across domains. So spanning from the long distance to the metro to the access domain, but as well across domains, across the transport teams and the data center teams. So really trying to make that openness happen this time. And I know as an industry we tried that several times between vendors. We haven't been very successful in doing this. But right from the beginning, at least this time, we are trying to use very open source software so that different people can come and participate in development of that controller. So a few examples of on how that can apply to transport applications. So we are going to develop 4 transport applications at the beginning. So the first one is a multi-layer PCE that is going to be able to compute the best path based on required SLA on a multi-layer network. So that's done by the SDN controller. We call that the Navigate application. The Protect one. The objective of the Protect one is to make sure that when you add a new service to the network, you are as well having the restoration capability to protect it, and that you will be able to avoid contention. Because as of today, there is some restoration plan in the network, but very often you have a very high contention when you are running things things like fast reroute, it creates contention on the network. This will help pre-plan the restoration of services to avoid contention. This one really is getting deployed now. It's a bandwidth on-demand application. We are deploying it with Equinix, very big reference. And this really allows the end user to request bandwidth on demand. I'll go through this in a moment, in a few seconds. And the last one is really looking at optimizing the way services are routed across the network. Because as you know, there is always some churn in the network. You're adding sites, you're deleting bandwidth, you're adding bandwidth. And at the end, after a few years, the way the services are routed or were routed at the beginning is not efficient anymore. So this application is taking a step back, looking at, okay, are those services, are they routed the best way with the network the way it is today? And it will propose to optimize the way those services are routed. So just touching on this bandwidth on demand application. So really the idea here is to leave the capability to the end user to request bandwidth on the networks in a pre-planned way. So now your end user is going to be able to go to the system and say, okay, I have this data transfer to do. I would like to do it tomorrow at 2 in the afternoon, and it will last 3 hours. And I need 1, 2, 3 gig, 10 gig, 100 gig to do it. So the system will check if the capacity is available. It will try to find that capacity, it will reserve it, and when the time comes, and only at that time, it will reserve the capacity, give it for that application, and release it for someone else to use it later on. That's one way. The other way, on the right side, is that we start automatizing this with data center applications. For example, with Brocade, and I have some Brocade is down there, so I'm not sure if there is someone from Brocade, so keep me honest if I'm saying bad things. But so Brocade has an application, the ARD, the resource broker, that in case in the data center you need more virtual machines or storage capacity, it's going to look into the network elsewhere in other data centers where it is more efficient to add virtual machines. So now when it's doing this, is going to require as well, so it will do this at the Brocade network elements level, and it's going to require bandwidth from the network, so that now you will have a required bandwidth as well to reroute the services that were going from the end user to that virtual machine to another virtual machine. So making sure that that connect portion is now as well in place, so that this move of virtual machine doesn't impact the end customer. So, and this gives a few additional information on how we can handle this. So just my last slide on this. Where are we really? So as I said at the beginning, SDN is really evolving as of today. So last year we started doing experiments, and we did that with a number of research and education networks to start experimenting how software-defined services were handled. This year we are introducing layer 1 and layer 2 SDN applications, those 4 applications that I've discussed, on an open daylight-based controller. Going forward, next year we will increasing to address the full layer 0 to layer 3 multi-layer capability, and we'll be doing that, by the way, with Ericsson, with whom we are partnering for the layer 3 capability. So we are doing some hopefully good progress in making that move towards more agile networks, both at the infrastructure layer and the software layer.
Thank you very much.
Thanks.
We have time for one question. Come on. You had coffee. One question for me then, Christoph. Thanks for an interesting presentation. You showed on your slides 400 gig. Phase 1, phase 2. Phase 2 is limited from your slides, to 1,200 kilometers as we speak. The world's oceans are longer than that. You elaborated on the fact that piece of the spectrum you will be able to do 400 gig across oceans. As you probably know, Nordunet and other advanced NRANs are doing 100 gig across oceans right now. Are we limited there? Do you think that 200 gig across oceans will be a real big challenge?
So yes, absolutely. And again, the Shannon limit is really showing us this, showing us that when you increase the spectrum efficiency, then you have more and more requirement to have a high OSLR. So there will always be a limit in terms of reach on what you can do with those very high modulation scheme and very packed capacity per spectrum. So the expectation is that for submarine networks, we will probably keep with 100 gig for quite some time. But the next step that we want to do in submarine networks is nevertheless pack more bandwidth using super channels, and this is what we are introducing now. So more 100 gig in less spectrum nevertheless.
Okay, understood. Thank you very much. Once again, thanks.
Maybe there is another question, but maybe we don't have time for that.
We had time for one. A quick one, guy.
Okay, I'm interested in, you've got OpenFlow on your diagram. There's interface into the equipment. And I guess the standardization process for transport OpenFlow is still ongoing. Do you have any feedback that you can give us on, I guess, your involvement in that and how you see that progressing? Do you have a preference towards extending the wireline OpenFlow as it stands for transport, or are you interested in some REST-based protocol for transport OpenFlow? So, what's your involvement?
So I guess we are very pragmatic regarding this. So first, the transport OpenFlow is being progressed within the ONF, the Open Networking Foundation, and actually Sienna is chairing the work group that is looking at the transport SDN, so moving that transport OpenFlow forward. So release 1.3 of OpenFlow is introducing the very first basic aspects of transport OpenFlow, something that is going just to be used for demonstration, first trials. We expect more features to be available in release 1.5 probably at the end of next year. So what are we doing in the meantime? Well, in the meantime, anyway, let's be pragmatic. All those networks elements out there don't speak OpenFlow anyway, right? So what you can do is to have plugins into your SDN controller, and this is what is shown here with TL1, CORBA, SNMP. That will do that adaptation with between the protocol that is being spoken by the network elements and the SDN controller. So in the first phase, and for the next 12 months at least, we will be using this. We'll be using as well netconf, which applies more to the data aspect, but we are moving to packet optical network elements. There is a lot of interest in netconf. So definitively, when transport OpenFlow will be there, we'll probably go there. In the meantime, we have other ways to do this.
Okay, thank you. And I'm sure you'll find each other offline when you have more information about that. I'd like to go to our last speaker for this transport networks session. Our last speaker is Lars Langebjørn, my colleague at Nordunet, who works for Nordunet since 2007. Lars has an extensive experience in dealing with SDH and DWDM systems for 15 years now, and he is the network engineering and planning manager at Nordunet. And he's going to talk about what Nordunet is doing in introducing 100 gig transmission in our network, and what we do in OTN in the Nordics. And as soon as Lars is wired, the floor is his.
Hello, yes, I'm on, good. 5 years and 7 days ago I held a presentation in Copenhagen where I presented the new Nordic network at that time. That was the Alcatel network. And that was based on web selected switches and 10 gig channels and so on. And we talked a lightly about the new things that we could do with that network. We talked about maybe that we could control the wavelengths, we could do alien wavelengths. We talked about channel capacities reaching 40 gig, and there was a small talk about 100 gigs as well. So that's 5 years and 7 days ago, and at that point it was not mature technologies that we were talking about. Today, now 5 years later, we have those technologies are mature, and I'm here today to present the new Nordernet network, which is based on those technologies. I know Edward Snowden has a patent on prison network stuff, but actually Nordernet was first with that. So we are still proud and we still use that name for our network. Today I want to present here the background for the network and the network itself, how it looks and topology-wise. Then I will talk about what we call optical or network integration that Nordernet has preached for maybe 5 years, which is the common use of our optical infrastructure in the N1 world, and see what we can do there. And then the new services that we are able to provide to the Nordic N1s, because after all, this is what the Nordic N1s will get. That's what they see, that when they order something, we will provision something. So that's where we are going in the next 20 minutes. First of all, say that this project started some years ago. We called it NDN2014, and it was about ensuring that Nordernet had the network that would be sufficient for the Nordic N1's needs up until and hopefully a little bit beyond 2017. What we would like is that it should be supporting the N1s, yes, and our continued peering infrastructure, and 100 gig, it should be supporting that as well and beyond. And switching, and protection, restoration should also be included. At that point we didn't know which technology we would like to use, but we would like to make sure that the 10 gig services that we were providing were in some way protected. What we saw was that fiber cuts were the predominant cause of interruptions at that time. And then we should expand our infrastructure where it made sense. So the status of this is that we actually are done with everything, and these are the main things that is part of this network expansion. Peering is expanded. Frankfurt in the US, for example, we have new fiber tenders done where we are extending the network or consolidating our network in Hamburg with 2 new tenders for fibers. We also have a direct fiber now going to London, and we have procured also fiber between Amsterdam and London, enabling us to have various protection for our network. So the network looks like this. It has expanded considerably in length now, and yeah, almost 7,000 kilometers. The green network is our own fiber and our network on top of that. Yellow is what I call shared operation, where we own the fiber and SurfNet is actually operating the boxes on top of that. This is a good way of doing it, especially that we have enabled that SurfNet has, or the N1s now have a uniform network going from London and all the way to CERN if you would like that. And then we have the orange stretch, which is served with alien wavelengths. We have optical equipment both in Hamburg and in Amsterdam, but it's SurfNet that is running the equipment on the stretch between those two cities. And again, this is the integrations that we have talked about. This is what we have spent 5 years on together with SurfNet, is to investigate what can we do with alien wavelengths, to what extent can we do this, and we are now deploying this as an integrated part of the network. This is not just for fun anymore. This is our core network that looks like that. We are running protected services through the yellow, orange, and green lines seamlessly. So this is, I think, is a big win for the network. Similar, if we look a little more detailed on Sweden and the topology there, The red lines are the Nordnet network, and they do cover quite a big part of the southern Sweden. And what we would like to achieve, and what SUNET would like to achieve, is that we have some kind of possibility to interconnect with SUNET at specific places, so we can. The blue line is a mesh line that we hope to establish in the coming years, but it could also be the blue points that we have there, where we could pick up traffic from SUNET directly in the optical layer. Especially we have Halmstad and Malmö in the south, where we are expecting traffic from the new European what's called ESS project that is supposed to be done. We need to be prepared for that. The other places are Örebro and Gothenburg, so we can interconnect with that. In order to achieve that, we start on, we have designed those 4 sites as what we call the super amplifiers. It's looking like this, where we from the start has integrated WSS components, so we are prepared for an expansion of the network, enabling us to accept those wavelengths without any interruption. So this is a non-disturbing rebuild of the network. The current proposal right now is that we make a multi-degree node and then we have another WSS component dropping the traffic and treating that it's treated as a client. That means it leaves our optical network and our domain and goes into another domain, and that can work, of course, only if the other domain is accepting alien wavelengths, and we accept alien wavelengths from that point there. So this is the current design that we are working with. Expanding that to local drop, we can add an additional WSS and a drop ports that can drop traffic or add traffic in all directions. So this looks very good on paper, and we are actually deploying something like that right now. Our fiber going from Hamburg to London is passing through Brussels. And in Brussels we have SurfNet, and we have now sent this for verification with China and checking out if that is possible to interconnect those 2 node types. Sorry for the color mix here, but the top one is now SurfNet. SurfNet is in the data center one place in Brussels. Then we have 10 kilometers of fiber going to the blue data center, which is Nordnet. And here we are looking into doing exactly what we have preached here, that we want to interconnect seamlessly on the optical level and enabling entrants from various countries to, for example, inject wavelengths in London, be able to exchange traffic or cross traffic in Brussels, go to Geneva or go back to Amsterdam to create protection for our sea-links. We have some sea-links going from Amsterdam to London, and the repair time is usually a couple of days, so it would be nice that we had optical protection through Brussels. So this is going on right now. Yeah. Then for the entrance, probably, our main technical requirements. We would be able to deliver 100 gig. That was one of our requirements for the new network, to all involve points of presence. And we would like the maximum control of the optical spectrum to enable this network sharing. And then, of course, the alien wavelength support. On top of that, we still believe that there's room for 10 gig services, although the new de facto standard for wavelengths and maybe also for core routers is 100 gig. We still believe that individual service offerings should be 10 gig services, or will be for a considerable amount of time for the different projects that we help. So also that the current services that we are deploying, and many entrants are deploying, is 10 gigs through transponders, and that means a lot of cabling, shipping back and forth transponders, and a turn-up time that is considerably longer than what the previous speaker talked about, that we could set up services within a few seconds, maybe controlled by software or other applications. So what we looked at is OGN, but a little more about that later. This is the new traffic matrix that we have achieved with dual polarization QPSK. And there's only a few red spots. The red spots are from Tulegarden in Stockholm to London, which we call HEX in this drawing here, and then from Finland. And that means that we can achieve that regeneration somewhere with the red spots. But otherwise, everything is covered. Even the fourth line, you and I going to London, that is actually established now, and that's around 2,000 kilometers that is running. So that is already in the network. Enabling other modulation formats, then the traffic matrix looks like that, where the orange is dual carrier, and the blue one is 16 quad. And deploying that on top of our current network, there is no place that we cannot reach without regeneration. The dual carrier approach, as you said, maybe 14,000 kilometers. I think in terrestrial designs, maybe 6, but it really depends on the number of AMP sites and patches and so on. But it would, with the Brussels connections there, we are making with certain, in principle, we could go from Helsinki all the way to Geneva, maybe. That's a real achievement, I think, for the optical network and for the idea of network sharing. So this is how it looks today. About the OGN choice of multiplexers that we have below this fine optical network. Well, OGN, usually when we talk about that in the animal world, they look and say we don't need OGN, but OGN has been there the whole time. It's just been on the lower layers, you didn't see them. So we still believe in that and deploying that, and combined with the OGN, we have requested an intelligent control plane that would enable us to turn up services very fast and have restoration and protection directly in the network. It's a little bit difficult to check or to show you how fast this actually goes with the provisioning. This is actually about when you give an order, put an order for a new service from Nordnet, how fast actually you can do this. Yeah, it's difficult to show that. This is the screenshot of the provisioning of a sending service. And here it is important to tell that we are talking with the control plane and the nodes directly. We're not talking about an offline database that keeps an image of the network. This is taken directly from the network, which means in the provisioning time is much faster, and the resources are available. So in the top of it, we have just selected the client speed, and then the node it goes from, and then the port that we can do it from, and then the destination endpoint. That's actually it. Then we know that there are resources available on the different nodes. And then in the next window for this provisioning is the control plane settings that we can set up here with cost criteria, mesh restoration criteria, and reversion and transport mapping. This really is a big step. I don't know how many of you that has operated with other management systems, but this is really fast turn-up times of this. So the result is something like this. This is taken from the management system, and that is turned up within a few seconds. And the intelligent control plane also detects, of course, the fiber breaks and so on. In the top part of that screenshot is our fiber or our connectivity between Hamburg and London. And if we encounter a fiber break there will be a switch of this service without any need for user intervention. It would go very fast. So in principle, it would look like this. And this has occurred. There has been fiber errors already on the new network, so we know it works, and it works quite good. Yeah. How far are we with the network? I think I would like to give a status on that. So this is the status of the new network, the Shenna network, as we speak. All the green points are in operation, in service, and yellow parts are installed, and the red parts are unfortunately a little bit delayed. I have to say it's not the fault it's not technical faults that are delaying us, it's actually logistics and VAT discussions with Norway and stuff like that. So the actual rollout of the network has been going really, really smoothly. So that was actually it. It's my time, right? No?
Thank you very much. You're quick as always.
Yeah, too quick maybe.
Thank you very much, Lars.
Thank you.
We do have time for 1 or 2 questions for Lars. Yep, I see 2. Microphone, please wait. Here you go, guy.
How far back?
Yes, this one. Okay, so that's good. So you've got Hamburg on the right. And what's the town on the top there? This one.
This is Hamburg 1. We have 2 nodes in Hamburg.
Oh, okay.
And this is Hamburg 2. And this is, you can say, it's a logical link. This is an OGN link that is going between, but the actual fiber is going like this, going and passing Brussels. So this is the fiber route, and this is the virtual circuit that is going between those 2 nodes.
Okay. And that's Amsterdam at the bottom.
Yeah.
Okay. And there's also fiber, so there's SurfNet fiber which goes...
The SurfNet fiber is this one actually, and it's represented by an OGN link going between those 2 nodes.
So I'm thinking the fiber that goes down to CERN.
That must, yeah, I mean, sorry for the topology drawing, but it's here.
Okay. and it goes through Brussels, so Brussels is a flexibility point that cross-connects your London to Hamburg with the Amsterdam through to...
Yeah.
And that's a flexibility point based on the WSS.
That's the WSS complex that we showed there, where we are setting up those 2 more or less identical nodes back to back, but we're not interworking the management domains, which would be a little more complicated. So the waves are dropped as a client and received in the other end as a client. That means it's not looking like a line signal, but it is. Making it easier to operate.
And so you pick up services in Hamburg, the 2 Hamburg sites, do you? So their service access points Amsterdam and London, but Brussels is not.
Currently, Brussels we don't have drop capacity, we don't have OGN switching, but that can be expanded. The node is built so it can be expanded like the other nodes that are shown, the super amplifier, whatever we call it. It's prepared for that. So. It is because there's 2 data centers in Brussels, and our fiber provider went through one of them, and the other ones are at another site. So,
I guess so. Am I allowed to ask some more questions? All right. So, in terms of the sale of services at those points, who do you make those services available to? Who are you prepared to sell, say, wavelength services to at those?
We are open as always, Guy, for anybody, probably not commercial companies, of course, but we have been preaching this, that we could share the resources and also invest the time and efforts in doing that.
Okay, thanks.
And to quickly add to that, NordNet has no ambition to deliver services to Belgian universities.
Maybe while you were walking up to here, I can tell that yesterday maybe you saw at René's presentation that we talked about ANA 100, and that those 2 circuits that are serving US is terminating in Amsterdam and London. But to enable this ANA switching complex that is expected to be a reality, we would like to close the gap between Amsterdam and London, and that will be done through both Brussels and the Amsterdam London to ensure that we have redundancy. So also for the ANA, this is an integrated part, the Brussels point.
Yeah. Okay, Henning had a question. You're next in line.
So thanks for the very interesting overview. I have one question on OTN. Which kind of OTN cross-connect capacities did you deploy?
The switching capacity.
Switching, real OTN switching capacities.
3.2 gig.
In total, all over the network?
No, I can't remember exactly. But it's present in all 12 core points that we have. Maybe I didn't understand the question correctly. But
so there are OTN cross-connects deployed along with the optical interfaces and the WSS technology?
Yes.
Thank you.
Okay, we have time for one more question. Okay, I'd like to ask one small question, Lars.
Yeah.
I remember back in Bruges in 2008 at the Torino Networking Conference that a few of us sat together and I think we had coffee and we had a napkin and we drew the concept of an alien wave on that napkin. That was 2008. We are now, 6.5 years later than that. You showed in your presentation that Nordnet actually is deploying that in production. What would you say are the 1, 2, or 3, whatever you'd like to answer, 1, 2, or 3 most difficult things you found when working with alien waves?
I think the most difficult is also it is the operation of the alien wave and agreeing how you operate it together with another inland or another partner. We usually have a lot of bandwidth available in the N1 world, and there's a lot of unused spectrum. So the actual interworking between the wavelengths, I don't think that will be a big problem. We have enough spectrum so we can put in guard bands if we want. But I really think it is the agreement that has to be made between the operational branches. And then I think we should invest more time in, for example, having a portal where you can exchange the up and downs of the alien wavelengths and the services that are interrupted. So we have done that previously on other layers, N2N1 I think it was called. We could do something again on this for the alien wavelengths and network sharing.
Okay, so this can be still work in progress and more innovation to deliver this concept. Okay, thank you very much. Join me once more in thanking Lars for his presentation. Thank you for being here. This concludes our transport network session here at the Nordnet conference in Uppsala. It's time for lunch now, and before you go, I have one more remark to make. Tonight there's the gala dinner starting at 19:30 at the castle here in Uppsala. You had to register for buses in order to be on one yesterday, but I just heard from the reception, the conference reception downstairs, that there are still a few more places available at the buses, so don't run there, but you might be lucky if you still want to register for the bus. And if you're unlucky or you want to walk, it's a beautiful walk there, and I think the weather is still nice. Thank you for being here. Enjoy lunch.